Okay, so we are going to talk about clutches and brakes. What is a clutch? In Chinese is 离合器. Okay, if you don't know. So brakes is 刹车, right? So they are usually materials that is going to be sacrificed, and we use it to transmit our power from one side to the other side. If you are treating this material as a clutch, if it's a brake, basically we, because one side of the structure is stationary, basically not moving. The other side is moving, basically like our wheels. So if you put a stationary object with a moving object together by some sacrificing material, which is the brake, you can stop the moving object. But some wear will be occurred on the material. So now, today we're going to learn about how the wears are going to happen in clutches or the brakes. So, let me show you. Okay, so this is the like a ring type clutch. Okay, so there are some materials surrounding the inner structure, and they have some linkage design. So the structure expands until this soft material has contact with the ring on the left hand side. So your if you have a motor on the right hand side, that you can then drive the left hand side, because the friction between this clutch and the outer ring allows you to drive the force from the right to the left. But these materials will be, you have wears on those materials. 磨耗. Okay. So how the next issue is, how do we compute the wear inside the material? There are two kinds of models. So before we start, let me let you know what are the two kinds of models. So if you have a piece of either clutching material or brake material, and this is one side, this is the other side, and you have contact, and let's say you have friction over here, right? So usually you need to apply some pressure, and the amount of wear at the interface depends on, has certain models. So one model is called the constant pressure model. So in certain geometry, you can assume, okay, the pressure applied to the entire interfacial surface is constant. Okay, does that mean you have constant wear? Depends on the geometry. That's why we need to do some math. And the other kind of model is called the constant wear. So you assume the amount of wear everywhere is the same. So the material removal at the interface, the speed of the material removal at the interface is the same all for the entire surface. Okay, so does constant wear means constant pressure? not necessarily. So usually when they try to build up some kind of model, like a physical model, they have certain assumptions. Those usually are two kinds, and depends on the geometry that you are working on. Okay, so for this particular case, there is a thin layer between the inner structure and the outer structure, and they try to study in this cylindrical coordinate, right? And they make a small cut, and the small cut has an arc length of radius times the small increment of theta. So just a tiny area, okay? So what do? They start to follow certain geometry, okay? Follow geometry. So right here, they are trying to let me see, where is the delta? So by geometry, this is perpendicular to, so they are, from the mechanism, there is a support right here. So they are trying to study everywhere around this arc. So because of the geometry, and there is a driving force that is perpendicular to this investigated position toward the joint. Okay, so let's see, half of the sine. This is cosine, so here is the sine. Here is the sine half of the theta. This is half of the theta by geometry. I try to compute this part, and this is the part I want to talk about. So for everywhere, there is at every particular point, you basically have a normal force. And the normal force, because just like our pulley, you have to assume the normal force could be different everywhere because of the geometry. So they made a small cut and they treat the there is a small increment of the small part of the normal force, and you will have a, depends on how the outer ring rotates. So there's a friction force. So let's say the friction force goes this way. So the friction force will be equals to the friction coefficient times the normal force. Okay, and then you will have reaction forces at point A, and you have applied force. So you have a geometry, you have a mechanism that drives a force applying from your mechanism. You have a driving force pushes your clutch toward the inner ring. So you want to solve for this force balance. And because this geometry is complex, so the investigated position has different load condition everywhere around the entire area. So they basically focus on one small area and try to use geometry to find the radial component and also the tangential component. Okay, and since from this geometry, it will be easier if you investigate along the XY coordinate, because they want to study the reaction forces along the XY coordinate, not the polar coordinate. So they know the normal force is going to be going through the center, and the friction force is going to be perpendicular to the normal force, and it's not parallel to your XY. So you need to use geometry to find out what would be their XY components. Over here, they are investigating at specific angle theta. Theta ranges from theta 1 to theta 2. So this is like one part of the clutch. So later on, when you do integral, you basically integral from theta 1 to theta 2. Now, for the from geometry, you realize this is theta and this is theta. So this one will be dn times cosine theta. This one is dn times sine theta. And for these two, they will be, this one is f dn cosine theta. This is f dn sine theta. Then you have reaction forces here. You have a driving force here, and because you have a support, so you have a driving force that is perpendicular to your arm from this point to this low position. So this is, if you draw a line from this point to this support, the driving force is perpendicular. And you can also get the XY component of this driving force. Okay, so from here, we did some calculation. So the let's see, where's PBR? It's from the geometry. The theta is the arc length. So force over area equals to force. So if you have if you draw the thickness of this material, we already know the arc length is r d theta from what we had right here. R d theta is the arc length. Then B would be the thickness right here. So the area, if you have force over area, area is B r d theta. Then you have pressure. Okay, so right here you have dN times, so P right here is pressure, B r d theta. And from what was from the model, actually this is from the model, PA. So the pressure distribution inside the material has this model. Okay, so we have to pressure equals to pressure PA over, so this pressure, P should be the normal one. P is the normal one. So PA would be, let me figure out. PA would be along the, let's see, PA. PA is the largest pressure. So from here it's trying to tell you what is the, when does the largest pressure happen? When does the largest pressure happen? And P would be pressure at any angle. Okay, so from here it's telling you at 90 degree, you have the peak. Basically, your driving force is perpendicularly applied toward the investigated area. So if you have this, if you have a geometry, and when you are perpendicularly applying pressure toward your material, so right here you have the max pressure. But when you are when your force is having a angle, so let's say you have your force is having certain angle against your normal direction, then your pressure won't be as high as the normal one. So PA is the max pressure. So over here is telling you that in that particular example, your driving force is not normal to your maximum pressure. So if you take a look, because it has a support point, so the normal direction and this length is never perpendicular. Okay? So the pressure to be computed requires calculation from here. So PA will be the max. PA will be the max pressure. And theta basically is the position you're investigating. So if you are located at the, if your theta is 90 degrees, then P equals to PA. Okay, if you are starting at the 90 degree, then P equals to PA. But what will be the pressure estimation at different angles? Then you use this equation to make adjustment. So over here, if you have a short material, then like the upper case, the range of the angle doesn't cover the largest, the 90 degree, then overall, among this area, the pressure is never the largest. But if you have a long material and within the material, there's a certain position where your force is 90 degree perpendicular toward the material, then you will experience the largest force. So from here, you just apply the model P replaced by PA times sine theta over sine theta A. So theta A right here depends on, this is a line, so you will never, if this is a long one, where is theta A? Theta should be, how do you draw? I think here is theta A. No, here's theta 1, theta 2. degree. So here. So here should be very small. So, oh, actually here is the, when theta equals to 90 degree. So this is theta A. So try to think about where is the position with the largest pressure. Right here is the force. Yeah, because if you are investigating somewhere here, so in this particular geometry, right at this point, you should have the smallest angle against the normal. Because if you move toward left, your driving force, let's make some drawing. in this particular case, you have your force right here. Then, if the material is right here, compared to this is your normal, right? Here it's actually this is your normal. So which one has the, how about here? Actually, if it's getting closer, it's having a smaller angle. But the arm is shorter. So there it would be some point where you have the largest pressure. Okay, so anyway, next will be trying to study the, so basically a balance of moment. Balance of moment. So the total moment equals to the moment that is contributed by FDN. So FDN is right here. And it has a arm length right here, R minus A cosine theta. Okay, so it is generating a clockwise moment. Okay, and what would be the other, there's an other moment that is contributed by dN. So FDN is contributing for the moment that is clockwise, and dN is contributing for a moment for counterclockwise, going left. So from here, also balance with the force times the radius right here. So in total, the clockwise moment includes Fc plus the clockwise one is F dN, and doing the integral. Well, basically they use the moment F, MF, right? Equals to the counterclockwise moment, so M by the normal force. Okay, that's why you end up with an equation like this: moment N minus moment friction equals to your force over C. So depends on different geometry. The moments contributed by the normal force and the moment contributed by the friction force may have different amplitude. Okay, you really need to do some calculation to figure out. And there will be a situation where you will have so-called a self-locking. So you have a positive value right here. So that means your force is the clutch applied to the inner ring and doesn't lose contact. Okay, there's always a positive force applied to the inner ring. so that you can have enough force that allows you to have proper connection between the inner structure and the outer structure. So when you design for this, when you design for the clutch, you want to make sure you have this self-locking condition. Okay, and this is basically computes for the required torque. Okay, required torque. So how do you compute the torque? So FRDN, total torque. So friction times FDN basically is the friction force times radius. So there will be a torque generated at the inner surface along the arc. And the torque everywhere is different because the normal force everywhere is different. Okay, so this is basically the model that doesn't have constant pressure. Okay, so the pressure everywhere is different. So you need to do the integral. Okay, and after calculation, you will realize, okay, that would be the torque generated at the arc. And by further calculation, it tells you what would be the reaction forces at X and Y. So you can use that to design your structure at joint A, whether your component at joint A is strong enough or not. Okay, so yeah, the rest are just calculation. Okay. So right here, there's an example. Okay. So in this case, it's a brake. It's a brake. So it has the diameter in 300 millimeter, and there's a mechanism that applies same force F on both sides, and then the left and the right are identical, and there's a phase width of 32. So basically, right here, this B is 32. And the coefficient of friction is 0.32, and the maximum pressure is 1,000 K, basically 1 megapascal. So it asks you to estimate the allowable applied force and the reaction forces. Okay, so let's take a look. So from geometry, first they try to calculate distance A. Distance A is the distance from the joint, from this joint to the center. So from geometry, basically is this is A. And basically square root of 112 squared plus 50 squared, like this. Okay, computing distance A. So just apply the equation, the driven equation. The moment for the friction force equals to this equation, and they just plug in numbers. So over here, friction coefficient has been determined, and it's already giving us the thetas. So from here, theta 1, this is theta, oh here, it's telling you theta 2 is 1, 2, 6. So treating this joint as 0 theta, so the other edge would be having 1, 2, 6. And if you treat like we studied, the maximum at when theta equals to 90 is giving us the largest pressure. So plugging in all the numbers, PA is given. So the largest pressure that you can have. And then B basically is the width. So right here, B is the 0.032. 0.032. Like, oh no, yeah, also 0.032 right here. That's the B. Radius basically is 150, I think. Yes, so 0.15. Okay, and friction coefficient is 0.32. Sine theta A is 90 degrees, so sine theta A is 1. And so basically plugging in, theta 2 is determined, A was determined, radius was determined, so everything was determined. So this is the moment due to the friction force. Now, another equation is the moment due to the normal force. Everything was mentioned, so just plug in numbers. At the end, the actuating force equals to the equation that was mentioned earlier. So since we are studying based on PA, so the maximum allowed pressure, so the largest force that you can apply is given right here. So if you apply even greater force, then your maximum pressure will be larger. That will violate what the problem is asking for. So if you use PA to compute everything, at the end the F would be the largest applied force. Next would be trying to study the torque that is generated by the brake. Okay, so how much torque you can generate to stop. So over here, they follow the calculation to compute the torque on one side. But there's a difference because the left and the right won't be the same, I think. Because, let me see, the angle is different. Let me see which one is different. 4 P. Same equation, but let me see which one is different. 443. So the PA on the left hand side is different. Question 16-2. Let's see what's 16-2. Because of geometry. I think the issue is the friction force is on the other side, on this problem, if it's rotating this way, then the friction force would be fighting against it, going left on the right hand side. But for the left hand side, it's also going counterclockwise. So even though the geometry is symmetric, but the friction force is always fighting against the geometry. So if you directly mirror the math, the friction force are following the different direction. I think that's the difference. So if you apply, when you do this, let's see what is affected by the direction of the friction force. Basically, you will have like a negative F. So can you directly say plus right here? Let's see how cannot be friction normal plus left 788,304. How to do 788? I think they already did some calculation to come up with the result. Yeah, right here it's plus. Earlier it was minus, is it? Like I said, it's plus for the left hand side. Because earlier, when we do the balance of moment, the moment contributed by the friction force is going clockwise. But when you mirror this whole thing to the other side, and your friction force is still going clockwise, if we are in this particular case, then the friction force is going clockwise. So when you mirror to here, the friction force is actually on the opposite side. So it's actually giving you negative sign right here. That's why at the end, your overall equation looks like this. Okay, and that's why the required torque, the resulting torque for the left hand side is slightly different. Okay, so but even that's the case, the brake on the left hand side still contributes certain amount of torque. So if you have this kind of geometry for braking, now you know the torque that is generated on both sides will be different. Okay, so that implies the wear of the brakes on both sides will be different as well. Finally, it's basically the calculation for reaction forces. They just plug in the numbers. Okay. So overall, at the end, they computed the Rx and Ry and then compute the final reaction forces. So you will realize how much reaction forces are being applied to the joint, to the pins. And for the reaction force on the right, because there are more torque, and it implies there will be greater reaction forces. So you can see for the right-hand side brake, the force is larger, and for the left-hand side is smaller. Okay. So that would be the result. Okay. So it's great that they made this drawing. So when you apply the same amount of force, because of how the wheel rotates, the reaction force on this joint is much larger than the reaction force on the left, even you are applying the same amount of force. And the torque you generate is stronger right here and is smaller right here, just because how the reaction for the friction forces follows the same direction. Okay. I would like to show you a different kind of brake. I hope it has it. This is more like a belt type. But I would like to, I would like to talk about the disc type. So for the disc, what's gonna happen is you don't brake from the parameter. You brake from the surface. So you actually, your force is not following the radial direction. Your force is on the side of the disc. Okay, so what's gonna happen is the torque that's generating along the entire surface is different. Depends on which radius you're talking about. The torque is different. Okay, so even you apply the same force and same pressure, the torque that's generating along this ring is different, depends on the radius. So the wear along for the entire surface is different. So right here is trying to focus on a small ring area at radius r with a small increment of r, dr, and trying to figure out the torque that's generating at this gray ring area. So here is the with uniform wear, second model. If you assume it's a uniform wear model, then the pressure will be different. So actually, there are different kinds of model to be used. Okay? So over here, so let me see. Pressure, if wear is constant, then pressure times the velocity is a constant based on the model that was given above. So in this case, because the v velocity equals to omega r, and omega remains the same. So PR remains constant in this particular case. So for pressure at any radius r equals to the maximum pressure PA times the maximum radius. Oh, no. D is the maximum radius. Oh, no, the smallest, small one. Because PR is constant. In this particular case, PR is constant. So where do you have maximum pressure? So when R smallest, then P is max. Right? So the pressure in the inner ring is the largest. So if you have a disc, a friction disc like this, then the inner ring has the greatest pressure. But right now it's following this constant wear model. So the inner part has the greatest pressure. Okay, so trying to compute the total normal force. So RDR would be no. If you have a ring, then this is R. The total arc length would be 2 pi r, right? So you will have 2 pi r here. And if you multiply the thickness, this is dr. So if you have 2 pi r multiplied dr, that would be dA, the area of the ring. The area of the ring. So over here, 2 pi r dr is the area of the ring. And if you multiply the pressure, that will be the total force on the entire ring. And if you do an integral from half of the small d, from here, to half of the large D, then you are computing the entire force applied on the entire surface. So the rest will be just calculation. How about torque? So what you need to do, it basically is using normal force times the so maybe I do it right here. So earlier, dF contributed on the ring equals to the pressure times dA. So that's why you have 2 pi PR dr. Okay? So the total force equals to the integral of dF. That's why you have that. But for the torque, contributed on the gray ring basically equals to the this is the basically dF will be the normal force times friction coefficient. That would be the friction force and times radius. Right? You need normal force, so on the ring, you have dF apply on the ring. If you multiply friction coefficient, then you will have the friction force apply everywhere on the entire ring, the friction force. And if you use friction force multiply the radius, then you will have the torque generated by the friction force. So total torque equals to the integral of basically integral of dt, and at the end you will have friction coefficient times dF. dF is right here, so 2 pi p. Here's another r, so r squared dr. Okay, so 2 pi f p r squared dr. Okay, so F is the total force that is applied to the entire disk. T is the total torque generated due to the friction force for the entire ring. And the rest are just calculation. Okay. So here, let me see, what's this about? Equals to pi p a over 4. Just plug in. Why do they want to express this in this way? Torque equals to that's a different model. This is uniform wear, but this is a different model. Earlier it was the uniform wear, model 1. So they want to do exactly the same thing for model 2, which is the uniform pressure. So how do we study the uniform pressure? Basically, torque is the same equation, and right here you can see the torque is the same equation, 2 pi fpa, 2 pi fp, but they apply the pa. So force equals to pi since the pressure is constant, so here is the total area. and pressure is constant everywhere. So F equals to pressure over total area. No. Pressure equals to force over total area, right? And what's the total area for a ring? Basically, pi capital D squared over 4 minus pi small d squared over 4. That's why your F, the force, equals to P times the total area. Basically, the pressure is the same everywhere. Okay, and from there, you can apply to the equation right here, and the P is now constant in the torque equation. So P becomes PA. And only thing that is changing is R. That's why only R squared remains inside the integral, and the rest are just calculation. So at the end, you found that with uniform wear model, torque is determined in this way. So you are assuming the torque is the same everywhere. But if you treat the pressure is the same everywhere, then the torque is different. Okay, so we can probably only choose one when we are trying to estimate the torque. Okay, so over here, here's a comparison. If you use the uniform wear model, that's the line at the bottom. If you use uniform pressure model, that's at the top. And for the ratio of D over capital D, and you will have a parameter along the y-axis. It's a normalized parameter, torque over friction coefficient times the force times the outer diameter. And over here you can see when small d is close to capital D, these two models are almost the same. So basically, if your ring is very small, your ring is very thin, there's no big difference. So if your disc brake is having a very narrow distance between small d and capital D, both models are almost the same, which means the pressure inside the ring is almost the same, and the amount of wear is almost the same. However, if you have a wider thickness right here, then both models behave differently. So what's the reality? Is it, if I have a wider ring, does my brake is gonna wear uniformly, or is the pressure going to be applied uniformly? Probably in between. Okay? Probably in between. So, there will be problems of the disc brake, and sometimes we don't have the whole disc, we only have a portion of the disc. But the calculation that we have done still can be utilized. We just need to figure out the right integral when we do calculation. So a lot of geometry. But from here you realize it's not only doing integral from theta 1 to theta 2, basically not only doing integral from inner radius to outer radius, it also, it's actually making a small cut, like small area. And it's doing two integrals. One integral is from the small radius to outer radius. The other one is to do integral from theta 1 to theta 2. Why do we have to do that? Because you may have variation along theta as well. You don't have an entire ring structure. You only have a portion. Okay, so what happened was you now have to investigate whether there's a difference between different angles. So if you are integrating from theta 1 to theta 2 and integrating from Ri to Ro, so you are basically making a cut right here. You are studying what's happening at particular small area. So this area is, so basically here is theta, here is d theta, and here is the investigating radius, here is dr. So what would be the dA? dA would be dr times the arc length. Arc length would be r d theta. So there must be a r d theta times dr. So r d theta dr is dA. dA times p is the dF. So you're doing integral of dF. So how about torque? Same idea. So dF equals to pressure at that particular point times dA, right? And the torque, d torque, equals to the friction coefficient times dF times R. Because at this particular point, you have certain amount of force applied to this point. So your friction force is along the surface, which equals to the friction coefficient times the small amount of force. And that friction force multiplying the radius would be the torque that is contributed by that friction force. So what you are doing basically is a complete integral so that you can get the total torque. Okay, the rest are just calculation. Okay, so I'm not going to go through the calculation. Just letting you know, if you have a portion of the ring as the disk, then you need to do two integrals. And the rest are just geometry. Oh, they use uniform wear model or uniform pressure model to show you how the equations is gonna look like when you do this. So then the rest will be just certain examples. I plan not to cover those. Similarly, you can have brakes in different shapes. Okay, and in that case, if you can do a ring type geometry, then you basically, from using calculus, you can do any geometry. So I'm not going to cover all of those. Okay, and clutches sometimes have working plans that is not parallel to your cylindrical system. Like this particular one is a cone. So there is the pressure now has components in different directions. Okay? So the chapter continues to introduce different kinds of geometry and let you know how the force analysis is gonna be affected. And in this particular case, as you can see, the pressure will have different components along the axial direction, along the radial direction, and also the axial, radial, and the tangential direction. So I think I won't cover all these. The concept-wise is the same. Concept-wise is the same, but it's much complex. And now you are dealing with a three-dimensional world. The force and the pressure are not in the same direction. Okay. So I just let you know, if one day you are working with designing brakes or clutches, and if it's not easily in a working plane or perpendicular to a plane, if it's along at some angle, then you may want to check the textbook. And also, there are concerns of temperature, because there will be energy loss due to temperature. Okay, so it's at the second half of the chapter. It also tells you, okay, your because there's friction, there's always temperature rise, your energy will be lost. So your entire power for braking won't be 100% contributing to braking. In reality, there are some energy loss. So it is trying to tell you the effect of braking at different temperatures. So if you are interested in the future, you can go check it out. I'm not going to cover all these. Okay, I think I'm pretty much happy about what I covered today. So just an overview. There are two major kinds of brakes or clutches. Just overview. One is the one that you have like a belt type that is surrounding a circular geometry. Either you have this soft material that is at the inner ring or outer ring. This is having a soft material contacting the inner ring of the left geometry. And it also shows different examples where you have brakes from the outside. Like this one is the brakes from the outside. So geometrically it's different, but computational wise, it's like you flip your normal force and your friction force. So this is one first kind of brakes where you have contact of your rotating object from the side surface, if you call it, or from the parameter. And the other kind basically is the brakes that you have this contact from the cross section. Okay, so two different kinds. And when you are, usually whatever you are trying to stop is following a polar coordinate. So when you have surface contact to a circular geometry, then the force pressure changes at different radius. So from the derivations, we realize if you are following so-called the constant pressure, constant wear model, then the pressure from the inner radius will be larger. The pressure from the outer radius will be smaller. But there is a different model where you assume pressure everywhere is the same. Then calculation-wise gives you different results. So when you compare them, you realize if the ring geometry is very thin, then there's no big difference between the uniform pressure or uniform wear model. But if you have a thick ring, then these two are the two extreme cases, whether you assume the wear is constant everywhere or pressure is constant everywhere. And I believe in reality, the wear is not uniform anywhere and the pressure is not uniform anywhere. So the reality is somewhere in between. Okay. So I think that would be the message I would like to share with you today. And let's check on the course schedule. Did I talk about welding already? So maybe tomorrow I will start to talk about welding. No, I don't think I talk about welding. So once I cover welding, let's check on the textbook. Let's see. So if you check on the table of content of the textbook, the second half of the book covers different kinds of components. We talk about screw already. Welding, not yet. So next time. Spring, we'll talk about spring. The ball bearing already. We didn't talk about lubrication. Lubrication basically at the end you check a lot of tables. So lubrication is very complex, and at the end, if you are looking for different levels of lubrication, you check the table. So I think I will cover that. Gears, we talked about gears already. And then clutches today. Belt already. Oh, we almost covered everything. And we also talk about final element. Okay, so tomorrow we will talk about the welding. Okay. At the end, we still have 1 week of, maybe next week we won't have, the welding part won't require this much time. So I will probably have some extra time for the course. I would like to share some knowledge with you about reliability. Because at this point, whenever we are designing something, we want ourselves to be safer. We apply the safety factor. So usually we have certain stress and we want this stress to be smaller than certain limit, and to be safe, we apply a safety factor at the bottom of the right hand side, so that we don't push ourselves to the extreme. That's the basic concept of this course, the idea of safety factor. But in different geometry, different components, equations are different, and you always need a mindset of safety factor. And that's usually the way. But from my personal research area, we realize that there are situations where you may have design choices that require multiple design choices that require consideration of reliability. So think of one axis. Think of one matter as along one axis. If this is the stress coordinate, and if you have a certain design, here is your design, and here's your upper limit. So why do we design in this way? Why do we pick up a design point somewhere that is a little far away from the limit? Because when we mass produce a design, it doesn't match what you are looking for all the time. There is tolerance. So in reality, whatever you desire to design will behave like a random distribution. So if you want your stress to be following certain level of stress, and if you mass produce 10,000 pieces, the stress mostly will follow your required stress, but there's a percentage where your stress will be greater and sometimes it's lower. So there will be a small chance, there is a percentage, there's a small probability where the stress of your design will be greater than the limit. There's a small percentage of actually so-called system failure. Okay? And this is basically you can say like a analysis of reliability. And does your system only has one matter that requires consideration of reliability? Maybe not. Maybe you have two matters. Maybe this is your coordinate, x and y. And here is one of your design. Okay, and maybe this is stress 1. And here is stress 2. Okay, and you have an upper limit for stress 2, upper limit for stress 1. So your design may have a normal distribution along the first stress direction, and also a normal distribution along the second stress direction. So in fact, overall, the random distribution looks like ellipse. So your failure probability is right here and here. So it becomes a multi-dimensional problem. So I would like to share with you how do you deal with multi-dimensional reliability problem. So that will be next week. In the future, you need to be aware. Most of the matters in a design may be dependent to each other. So whatever you do along the first dimension, that could be affecting the second dimension as well. Okay, so when I have time, I will talk about this. Okay, so it's more advanced, so it's just for you to know. Okay, that's it for today. If you haven't done the attendance check, you can do that. If you're done, then you're good to go.